In this tutorial, we're going to get practice with the equation for the period of an orbiting planet, also known as Kepler's third law of planetary motion. So imagine that we're dealing with planets outside of our solar system, extrasolar planets, going around some other sun. And specifically, we're going to deal with a real system, star system HD 47366. I couldn't have named it better myself. Here's the central star, it's just labeled A. And here's one planet labeled B and another planet labeled C. And the idea is that when I say star, the star is so much more massive than the planets that it's basically just sitting there at the center of their orbits and they're going around it like so. But they're going around with different periods because they're located at different orbital radii away from the star. Now imagine that we have determined observationally that the period of planet B going around its star is 363 days, where we're talking Earth days here because we need some well-defined standard for comparison, so 363 Earth days to go around star A. Planet C takes 685 Earth days to go around star A. And we also have information about the distance between the center of star A and the center of planet C, namely that distance is the orbital radius, which I call r sub c, 1.853 AU, where you may remember AU is an astronomical unit. That's the distance between the Sun and the Earth, so another standard. Okay, what we want to figure out are two things: the mass of star A and the orbital radius of planet B. So we ought to be able to analyze this system and figure out both of those numerical quantities. Let's rearrange our information here over on the left. And we're going to use information from our own solar system, because if we do this, it makes the calculation easier. So in our solar system, well, we know that the distance between the Earth and the Sun is an AU, so the orbital radius of Earth is 1 AU. The period of Earth, everybody knows that, it's a year. So we'll call that 365.25 days. The 0.25 is not that important, but it accounts for leap years. The mass of the Sun you may not know, this you would look up, and it's 1.99 times 10 to the 30th kilograms. The equation relating period and orbital radius and the mass of the central object is this, and remember that's also referred to as Kepler's third law of planetary motion. Okay, let's use this to figure out these quantities. Let's start with the mass of star A. Well, to do this, first let's just write down an equation that applies to system HD 47366, and that involves the period of planet C. So T sub c, the orbital period of planet C, basically the length of that planet's year, is 2 pi times the square root of its orbital radius cubed divided by big G times the mass of the central star A. Remember, the mass in this equation is the big mass. In this case, the star's mass is so much greater than the planet masses that we just have to put m sub A down there. Big G is a constant that we're going to factor out. We don't even need to know its value. We can write a similar relationship for the Sun and the Earth, describing the orbital period of the Earth, which is 2 pi times the square root of, now, the Earth's orbital radius cubed divided by big G, same constant, times the mass of the Sun. Now the reason to do this is that if these two equations are both true, and they are, then we can take a ratio of both of these expressions. Namely, if these equations are true, then the ratio of the left-hand sides must be equal to the ratio of the right-hand sides, like so. The reason to do this is that now we can cancel a bunch of things out. So we can cancel out the 2 pi's, that wouldn't have been that inconvenient to calculate, but we can also cancel out the factors of big G, and if you remember, the numerical value of big G is pretty far away from 1, plus you'd have it under a square root. It's very easy to make a calculator error in dealing with that, so let's cancel all of that stuff out. And we've done that. Now we can simplify this fraction. We actually have a nested fraction here with square roots. This is often where students make mistakes. First simplification will just be to make this an overall square root of rc cubed times m sun divided by re cubed ma. You have to be careful dealing with nested fractions. You may want to practice that. But now that we have this, let's square both sides, because ultimately we're trying to solve for m sub a. And now you can see how we can rearrange this to solve for m sub a, right? Let's multiply both sides by m sub a over m sun, and divide both sides by tc over te squared. So we do that, and now we have an expression for m sub a over m sub sun, and now we can put in the numbers, right? Because we know the values of rc, re, te, and tc. We figured all those out at the beginning. So we put in those values, and make sure not to forget to cube and square the appropriate terms. We'll simplify things a little bit on the right-hand side, and you notice that everything is unitless on the right-hand side. Well, that has to be the case because the left-hand side is a ratio of masses, so ultimately the right-hand side has to be unitless. Bring this up, and we'll enter it into our calculators. And we see that the mass of star A is 1.809 times the mass of the Sun. That's already one way of answering this question. You could just say that m sub A is 1.809 solar masses, but if we actually want a number in kilograms, then we insert the mass of the Sun, multiply it out, and see that the mass of star A is 3.60 times 10 to the 30th kilograms. So just by observing planets going around that star, we've figured out what that star's mass must be. Orbits are a great way to measure masses. The other thing we want to figure out now is the orbital radius of planet B. So let's move all this up. One way that you could do this would be to apply Kepler's third law of planetary motion, put in the value of big G. Now that we know the mass of the central star, you could calculate R that way. But I'm going to do another scaling calculation where we take a ratio to try and get things to cancel out. So this time, we'll deal exclusively with star system HD 47366. We'll write out an equation for the period of planet B and the period of planet C, and take their ratio. The strategy is very similar to what we already did between planet C and the Earth. The nice thing is, since both planets are going around star A, the factor of m sub A will also cancel. So basically everything cancels except the two orbital radii and whatever powers they're raised to. So we're left with TB over TC equals the square root of RB cubed over RC cubed. We can square both sides, and we want to solve for R sub B. Here you have to take a cube root, and you may want to examine your calculator carefully to make sure you know how to do that. Any scientific calculator ought to be able to handle that, but we'll take the cube root of both sides. And now we just want to go through and solve for R sub B, so R sub B equals R sub C times the quantity, TB divided by TC, raised to the 2/3 power, which is the same as saying squared and taking the cube root. Now we can put in numerical values. We know RC, TB, and TC, so we put all of those in, simplify things a little bit, and get that the orbital radius of planet B is 1.21 AU, 1.21 astronomical units, or 1.21 times the distance between the Sun and the Earth. This is a very common strategy for calculating star masses and orbital radii, so you do want to practice the approach of taking all of these ratios and canceling things out carefully.